4 billion years ago, Mars had oceans, real oceans, deep ones, covering almost a third of the planet's surface, with waves, with shorelines, with a sky that may have been blue. And then something happened, something so catastrophic that in the space of a few 100 million years, which is nothing geologically speaking, Mars went from being a world that looked disturbingly like Earth to the frozen, irradiated desert we see today. We know this happened. The evidence is written into the rocks, the valleys, the ancient shorelines still visible from orbit. What we don't fully understand is why. And what we've found beneath the surface in the last 5 years is making scientists very uncomfortable. By the end of this video, I'll tell you about a specific discovery from the Perseverance rover that almost nobody in mainstream media has covered properly. Something that changes the questions we're asking about Mars entirely. Let's go. Mars, the red and arid planet that we know today, had oceans, real oceans, deep ones, covering almost a third of the planet's surface, with waves, with shorelines, with a sky that may have been blue. And then the unthinkable happened. Something so catastrophic that in the space of a few 100 million years, which is nothing in geological terms, Mars went from a world that looked disturbingly like Earth to the frozen, irradiated desert we see today. We know this happened. The evidence is carved into the rocks, written in the ancient riverbeds still visible from orbit, preserved in the chemistry of the soil. What we don't fully understand is exactly why. And what we found beneath the surface in the last 5 years is making scientists deeply uncomfortable. Today, we're going through everything. The ancient Mars nobody talks about, the catastrophe that killed it, the geology that still breaks records, the water that's still there, just not where you'd expect, and the search for life that has produced one result the mainstream media has almost entirely ignored. By the end of this video, I'll tell you about a specific discovery from the Perseverance rover that changes the question we're asking about Mars entirely. This is not the Mars you learned about in school. Let's talk about what Mars actually was. Because the evidence isn't thin, it isn't speculative. The ancient surface of Mars is covered in features that can only have one explanation: liquid water, flowing, pooling, eroding, for millions, possibly billions, of years. There are valley networks, enormous ones, ancient river systems stretching thousands of kilometers across the southern highlands. These aren't wind formations. These aren't lava channels. The branching patterns, the erosion signatures, they are rivers. Full stop. There are deltas. Places where those rivers emptied into standing bodies of water and dropped their sediment load, exactly like river deltas on Earth today. The Jezero crater, where the Perseverance rover is operating right now, is one of them. We landed a rover inside an ancient river delta on purpose. There are ancient shorelines, visible from orbit, running along the boundary of the northern lowlands at a consistent elevation for thousands of kilometers. The kind of feature that only makes sense if there was a sea level, a literal sea level, on Mars. And there's the chemistry. Everywhere we've drilled or scraped the Martian surface, we find minerals that only form in the presence of liquid water: phyllosilicates, sulfates, carbonates, the entire mineralogical fingerprint of a wet world. Mars wasn't wet for a brief moment. Some regions show evidence of water activity spanning billions of years. Now here's where it gets interesting. This ancient Mars, with its oceans and rivers and thick atmosphere, existed at roughly the same time that life first appeared on Earth. The same time window. Earth got life. Mars got what? That's the question scientists have been asking for 50 years. And in the last 5, the answers have started arriving. But first, we need to understand what killed it. Because what happened to Mars is arguably the most dramatic single event in the history of our solar system. About 4.2 billion years ago, something in Mars's core stopped. The planet's magnetic field, which had been shielding the surface from the sun's radiation and solar wind, simply collapsed. We know this because of the rocks. Ancient Martian rocks are magnetized. They recorded the direction of the magnetic field when they solidified, like a geological compass. And those records show a strong, active field early in Mars's history. Then the magnetization disappears, abruptly. In younger rocks, nothing. The field died. And when it did, the consequences were catastrophic and irreversible. Without a magnetic field, Mars had no protection from the solar wind, the constant stream of charged particles blasting out from the sun. That solar wind began stripping away the Martian atmosphere, molecule by molecule. It didn't happen overnight. It took hundreds of millions of years, but the trajectory was one way. As the atmosphere thinned, atmospheric pressure dropped. And as pressure dropped, liquid water could no longer exist on the surface. The boiling point fell below the freezing point. Water either evaporated into space or froze into the ground. The oceans didn't drain into cracks. They literally evaporated into a dying sky and were stripped away by the sun. The NASA MAVEN mission, which has been orbiting Mars since 2014, has measured this process directly. Right now, today, Mars is losing roughly 100 grams of atmosphere per second to the solar wind. 100 grams per second, every second, for billions of years. The question scientists have argued about for decades is, why did the core stop generating the magnetic field? Mars is smaller than Earth. It cooled faster. When a planetary core cools completely, the convection that drives the magnetic dynamo stops. But the timing is the problem. Mars's core cooled unusually fast, faster than the models predicted for a planet its size. And some researchers now believe the answer involves a series of massive asteroid impacts early in Mars's history that disrupted the core's heat distribution. One catastrophe triggering another. A chain of events that turned a living world into a desert. And it raises a question that nobody can quite shake. If Earth's core ever cools, are we next? Before Mars died completely, it did something extraordinary. It built the largest volcano in the solar system, Olympus Mons, with a height of 22 kilometers above the Martian surface. Roughly 2.5 times the height of Mount Everest. Its base is so wide, 600 kilometers across, that if you stood at the center, you couldn't see the edges. They'd be beyond the horizon. You would have no idea you were standing on a volcano at all. And here's the thing about Olympus Mons that most of us miss. It got so big because Mars doesn't have tectonic plates. On Earth, the crust moves. A volcanic hotspot under the crust, like the one under Hawaii, punches through periodically, but the plate moves, so you get a chain of islands. The hotspot doesn't stay under the same point long enough to build anything truly enormous. Mars's crust doesn't move. The hotspot stayed in exactly the same place for billions of years. Eruption after eruption after eruption, all in the same spot, all piling on top of each other. The result is the massive volcano Olympus Mons. And Olympus Mons isn't alone. The Tharsis Bulge, the volcanic plateau it sits on, is 5,000 kilometers across and 10 kilometers high. The formation of the Tharsis Bulge is so massive that geologists believe it actually shifted Mars's rotation axis. The sheer weight of the volcanic material redistributed enough mass to tilt the entire planet. There's also Valles Marineris, the canyon system that makes the Grand Canyon look like a crack in a sidewalk. 4,000 kilometers long, 200 kilometers wide in places, 7 kilometers deep. It stretches across a quarter of Mars's entire circumference. If you placed it on Earth, it would span the entire continental United States from New York to Los Angeles. And we still don't fully understand how it formed. The best current theory isn't erosion. It isn't a river. It's that the formation of the Tharsis Bulge created such enormous stress fractures in the Martian crust that the ground simply split. A tectonic crack the size of a continent. Mars is not dry. I want to be very clear about that. Because the image we have of Mars, a completely desiccated, waterless desert, is wrong. Water is still there, just not where you can see it. The polar ice caps, to start with the obvious. Both poles have permanent ice caps. The North Pole cap is mostly watery ice, under a thin seasonal layer of dry ice that comes and goes. The South Pole cap has watery ice too, buried beneath a thick layer of frozen carbon dioxide. The amount of water locked in those polar caps, if melted, would cover the entire surface of Mars to a depth of 35 meters. But that's not the surprising part. In 2018, a team using the Marsis radar on the Mars Express orbiter detected something beneath the South Polar ice cap. A highly reflective layer at a depth of about 1.5 kilometers. The kind of reflection that liquid water produces, not ice. Liquid water. Briny, hypersaline, possibly mixed with perchlorates, but liquid. A subglacial lake, like the ones we have under the ice in Antarctica. Since then, additional reflective layers have been detected. Multiple possible lakes. A potential system of liquid water bodies beneath the southern polar region. Now, let's be careful here. Not every scientist is convinced. The same reflections can theoretically be produced by certain types of ice or clay minerals. The debate is ongoing. But if those lakes are real, they would be the most habitable places on Mars today. Because extremophile bacteria on Earth survive in very similar environments. In the subglacial lakes of Antarctica, in hypersaline pools, in environments with no sunlight, high radiation, and extreme cold. And there's more. In 2021, the InSight lander detected Marsquakes, actual seismic activity, suggesting the planet's interior is not completely dead. There is still heat, still geological movement, still energy, water plus heat plus chemistry. On Earth, that's a recipe we recognize. In February 2021, NASA landed the Perseverance rover inside Jezero crater, not a random location. Jezero was chosen specifically because it is an ancient river delta, a place where water once flowed into a lake and deposited sediment over millions of years. On Earth, river deltas are some of the most biologically rich environments that exist. Nutrients accumulate. Organic material concentrates. If life ever existed on Mars, a delta like Jezero would be the place to look. Perseverance carries an instrument called Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals. It's specifically designed to detect organic molecules and biosignatures in rock samples. In 2022, Perseverance found organic molecules in Jezero crater, complex carbon-based compounds, in ancient sedimentary rock, in a former river delta. Now, let's be precise, because this is where the media coverage gets sloppy. Finding organic molecules does not mean finding life. Organic molecules can be produced by purely chemical processes with no biology involved. They arrive on asteroids. They form in ultraviolet-driven reactions in the atmosphere. They are common across the solar system. What matters is the context, and the context here is unusual. The specific types of organics found, their distribution within the rock, and their association with specific minerals suggests they weren't deposited by a meteorite. They appear to have formed in place, in the sedimentary environment, in the delta. Whether that formation involved biology or purely chemistry is a question Perseverance cannot answer alone. That answer will come when those rock samples, which Perseverance has been carefully sealed and stored, are returned to Earth. The Mars Sample Return mission, planned for the early 2030s, will bring those samples to laboratories where we can analyze them with instruments 10,000 times more sensitive than anything we can put on a rover. The samples are sitting there right now, on Mars, waiting. And then there's the thing all the media entirely missed. In late 2023, a study published in the journal Nature Geoscience reported something that should have been front-page news. The InSight lander, which operated on Mars until December 2022, had detected, through its seismic measurements, that Mars has not fully solidified, not completely dead, a liquid outer core. The same feature that Earth has, the same feature that drives Earth's magnetic field. The difference is that Mars's liquid core isn't generating a large-scale magnetic field right now, probably because the conditions for the dynamo effect aren't quite right. The composition is different, the temperature gradients are different, but the liquid is there, and what that means, and why this is so important, is that our model of what killed Mars may be wrong, or at least incomplete. We assumed the core solidified, that the heat was gone, that Mars was, in every meaningful sense, a dead world below the surface. It isn't. There is still liquid iron in the interior of Mars, still heat, still movement, which means the story of Mars isn't over. It's just paused. And that raises a question that I think is the most interesting question in planetary science right now. Could a sufficiently large external energy input, say from massive asteroid impacts or from human-engineered processes, restart Mars's internal dynamo? Could we, theoretically, restart Mars's magnetic field? This isn't science fiction. It's a question geophysicists are now asking seriously. The Mars Sample Return mission will bring us rocks that may answer the life question once and for all. The rover will drill 2 meters below the Martian surface, deep enough to reach zones shielded from radiation where biological molecules could survive. We are closer to answering, was there life on Mars, than at any point in human history. And the answer, whatever it is, will be the most important scientific result of our lifetimes. Either Mars was barren, and we are alone in a way that should profoundly change how we treat the only living world we know, or Mars had life and died anyway, and we are living on a planet that is not as permanent as we like to think. Either way, it changes everything. Subscribe, hit the bell, tell me in the comments, do you think Mars had life? I'll read every single answer. Until the next mission.